بسم الله الرحمن الرحيم. المحاضرة السابقة وصلنا وناقشنا ال 5 basic factors that any arbitrary loop transfer function may consist of، يعني الأشكال الخمس اللي ممكن أي loop transfer function ممكن يتكون منهن. حكينا إنه الخمس أشكال هن عبارة عن اللوب جين أو الجين. أول واحد من الفورمز اللي هو الجين كي. بعدين حكينا اللي هي البولز or zeros at origin، وبعدين اللي هي real poles or zeros، والفورم الرابع اللي هي complex conjugate poles and zeros، والفورم الخامس اللي هو pure delay. وهذول هم الفايف فاكتورز اللي تأسس منهن أو اللي اللوب ترانسفير فانكشن بالصفحة السابقة كان متألف منهن. وحكينا إنه إذا عرفنا نرسم كل واحد من الفايف بيسك فاكتورز على حدة، بنقدر بعدين كونه عملية الماجنتيود بلوت والفيز بلوت عبارة عن جمع ل individual contributions أو المساهمات الفردية من كل واحد من هذول التيرم. نقدر نرسم البودي بلوت manual using approximate graph اللي هي بنسميها asymptotic graph، اوكي، بدون استخدام الكمبيوتر، ومنها نحكم على انه الاستابيليتي تبعت السيستم. فبالتالي اليوم راح نبلش بالفايف بيسك فاكتورز اللي هي اولا باول، واول تيرم اللي هو الريال كونستانت كي. طبعا الكي هذا جنرالي in most general case ممكن يكون الكي بوزيتيف او ممكن يكون الكي نيجاتيف. احنا بوضعنا الطبيعي الكي دائما بيكون بوزيتيف، بس ممكن بعض الحالات انه يكون الكي نيجاتيف. فاذا الكي بوزيتيف بتكون الانجل تبعته اللي هي زيرو، واذا الكي نيجاتيف بتكون الانجل تبعته 180 ديجريز زي ما هو مبين عندنا بالفيجر اللي هو 6.9. اوكي، يوم تكون الكي بوزيتيف بتكون الانجل contribution لهذا التيرم زيرو، ويوم تكون الكي نيجاتيف بتكون اللي هي minus 180 degrees. وبنلاحظ هون انه الانجل is constant whether it's 0 or 180 or minus 180 degrees. It's constant for all frequencies. اوكي، هذا بما يتعلق باللي هي الانجل او الفيز. طيب لو نيجي نحسب الماجنتيود بارت تبع for the constant k، بيكون 20 log الابسوليوت value of k whether positive or negative. ناخذ الابسوليوت value، وهذا الحكي بيكون constant. constant شو يعني؟ it's fixed for all frequencies. وهذا الحكي في له الكيس هاي الكي إلها 3 different possibilities. أول possibility إذا كانت الكي greater than 1 معناته 20 log الكي بيكون positive، وبالتالي بيكون عبارة عن يوم نرسمه بيطلع اللي هو zero slope line of certain value، وبكون هذا الحكي above 0 dB line above 0 dB. طيب الحالة الثانية إذا كان الكي بين الزيرو والواحد كماجنتيود بحكي، اوكي، إذا كانت الكي كماجنتيود بين between 0 and 1، okay, then also the magnitude will be constant but it will be negative in dB and it will be below the 0 dB line. Okay, the third case is when the magnitude of k is equal to 1. When we take 20 log k, it will be constant line with 0 dB. So we have 3 cases for the magnitude of any constant depending on the k, whether it's less than unity or greater than unity. And since we are speaking about the magnitude of k, we are not covering anything in the negative side because we are taking the absolute value. So k might be in the first case between 0 and 1, and in this case this magnitude, this contribution will be negative in dB. In dB will be negative, less than the 0 dB line. Okay, and at k is equal to unity, 20 log 1 is equal to 0, so it will have 0 contribution and it will be over the 0 dB line. And the third case, when k is greater than unity, magnitude of k is greater than unity, so the contribution of K will be constant, but it will be greater than this, the contribution. Okay, this is for example assuming that K is equal to 10, but generally it might be any value, and this will be above 0 dB line, and also here this is assuming that K is equal to 0.1, but it might be any value, might be 40, 60 dB or minus 40, minus 60. This is an example for certain K value, but the most important thing is the sign, whether K will be positive or negative or 0. And regarding the phase, K for positive values it will have a 0 angle or phase, and for negative it will be a minus 180 degrees. So this is the first basic factor of the 5 basic factors that we will cover. Okay, the second one is poles or zeros at origin. Poles or zeros at origin. So the numerator might have zeros, or the denominator might have the poles. Okay, so in general we are speaking about poles or zeros at origin. What I mean, s to certain power, whether this power is positive or negative, this means we have poles or zeros at origin. So regarding the magnitude plot in dB, we will take this 20 log of the magnitude of this term. Okay, and we take this n outside. Okay, and it will be plus or minus 20n log the omega, log the frequency. Okay, and in order to determine what's the nature of this line, okay, we will take two different frequencies. We will take two different frequencies. Like if omega, the frequency, omega is equal to 1, then 20 log 1 will be the magnitude of this term. The magnitude of this term, which is poles or zeros at origin, the magnitude part will be 0. And if we take a value of 10, then the magnitude of the term will be plus or minus 20 n log of 10, which is equal to 1, multiplied by 1, which is plus or minus 20 n. If we take omega is equal to 100, we will finally reach to plus or minus 20 n multiplied by 2, which is equal to plus or minus 40 n. So if we draw the values, those values 0, plus or minus 20 n, plus or minus 40 n, for the frequencies we consider pairs of data points. We consider pairs of data points, like for omega. Okay, for omega 0 frequency, it was for frequency of unity value, it was 0, and when the frequency was 10, it was plus or minus 20 n, and when the frequency was 100, it was plus or minus 40 n. So if we draw a line, okay, for this graph, only 2 points are necessary, but here we have taken extra points, so 2 points, they are sufficient. So if omega was 1, here omega 10, and here omega 100. Okay, so what's the value at omega is equal to 1? It was here, it was 0. So here, and for omega 10, assuming it's plus, we will use the positive sign. So it was like plus this point, it was plus 20n. And 400, it was also, we will use the plus sign, it was plus or minus. So this is 20n. This is 40n. So if we connect this line, okay, we will generate the slope of this line. The slope of this line, or before the slope of this line, we will discuss something that you have taken in another courses, the concept of decade. Decade is if we consider two frequencies, omega 1 and omega 2, and the ratio between them, like omega 2 over omega 1, is equal to 10, we call this decade. So here 1 to 10, it's 1 decade. 10 to 100, it's 1 decade. So what's the slope? Again, we will go back to the line. What's the slope of this line? Okay, we can, from this graph, we can calculate it, that it's in each decade, this one, it will give 20n. Or also for this decade, also it will give 20n. So the final result is the slope will be 20 plus, for this case, plus 20n. Okay, dB, don't forget that we are speaking about logarithmic scale. Here will be the scale will be dB per decade. Per decade. Okay, so this is the case of positive. If it was negative, it will be minus. So the final result is that this line will be a line of slope plus or minus 20 n dB per decade. Per decade means the ratio is 10 between two frequencies. So between two frequencies where the ratio is 10, it will have this plus or minus 20 dB. So plus will be for zeros if we have zeros, and minus will be if we have poles at origin. And this, if you remember, the poles at origin, we call it system type. System type. Poles at origin, we call it system type, and we use to give it the symbol of n. And this is why we are using at n, because rarely zeros at origin, they are rare case. They are rarely encountered, but poles at origin, which is the system type, they are frequently appear in transfer functions. So I will go back to our location. Okay, so we have proved that this will be a straight line, and its slope will be plus or minus 20 n dB per decade, and it should, when the frequency is 1, it has a value of 0 dB. So it should pass through this point at omega is equal to 1. It should be 0 dB line. So here in this figure, we will take different cases for poles and zeros. In this left one, we are speaking about a pole, and in this right one, we are speaking about a zero. So for single pole, sorry, let us start with single pole. This will be minus 20 n, and n is 1, so the slope will be minus 20 dB per decade. And if you notice here, at frequency of 1, its value is 0. And the phase of this one for any pole or zero at origin will be plus or minus 90 n. Plus or minus 90 n. Why plus or minus 90 n? Okay. If we consider that we have a zero at origin, which is j omega. So if we will plot this 0 in the real and imaginary axis, it will be located here. Okay, so whatever the frequency, regardless of the frequency, it will be always on the imaginary axis. Whether the frequency omega is 1 or 10 or 100, it will be always on the imaginary axis. And as we studied in root locus, the angle will be from positive real axis in the counterclockwise. So what's this angle? It's always 90 degrees. So if we have single 0, the angle will be 90. Okay, if we have 0 repeated, 0 at origin repeated of power 2, like s squared, what will be the case? Will be j omega to the power 2, which is equal to minus omega squared. Where's minus omega squared? It will be in this negative real axis. Regardless of the omega, it will be here or here or here. So it will be always on the negative real axis, this one. So what's its angle? It will be minus 180 degrees or plus 180 degrees. Okay, so similarly, if we have a pole at origin 1 over s, if we have a pole at origin 1 over s, what will be the case? So the pole will be here or here or here. It will be always on the negative imaginary axis, and if we measure its angle, it will be minus 90 degrees. And if we have two poles, okay, two poles, s1 over s to the power 2. If we have two poles, 1 over s to the power 2, then there will be, their location will be here, okay, regardless of their value, and it will be always minus 180 degrees. So we understood that single 0, if we have s single 0, it's 90. S to the power 2, it's 180. 1 over s, it's minus 90. 1 over s squared, it will be minus 180 degrees, regardless of the frequency. It's constant for all frequencies. So what's the general rule? The general rule is that it will be plus or minus 90 by n degrees. So n, if it is 1, it will be plus or minus 90. If n is 2, repeated, it will be minus 180 or plus 180. So this is the rule, and this rule is clearly written in the handouts. It's here. The angle or the phase is plus or minus 90n. Okay, so again, if we return to this figure, and regarding the phase plots, this one and this one, okay, for the pole, it will be minus 90. As you see here, it's minus 90, and it's fixed for all frequencies. And if it is 0, it's 0 here. It will be plus 90, and it's fixed for all zeros, for all frequencies, sorry. So this is the case of single pole or single 0, as obvious in here. So in the general case, as I discussed on the empty page before 1 minute, okay, so if we want to have more cases, okay, so if we will discuss the angle, okay, here, if no poles or zeros, okay, it's 0. If we have 1 0, 90, 2 zeros, 180. One pole, the angle in degrees. One pole minus 90. Two poles minus 180. And regarding the magnitude plot in dB, if you have 1, 0, it will be, if you calculate or check the slope, as I mentioned, it will be plus 20 dB per decade. If we have two zeros, it will be plus 40. If you have one pole, minus 20. If we have two poles, it will be minus 40. And if you pay attention, all of them passes through this point. What is this point? It's at frequency of unity, the value is 0, as I mentioned before. So I wish everything is clear regarding the second term, which are poles or zeros at origin. Let us switch to the third factor, which is real roots. Real roots at s is equal to minus 1 over t with multiplicity q. With multiplicity, they might be repeated. They might be simple real roots or repeated roots. And the root location is at s minus 1 over t. So if we calculate the gain in dB, it will be 20 log the absolute value of this term. And all of you know that 20 log will be, we will take this q outside the log, and we will calculate this, which is the square root of the real part plus imaginary part. Okay, it's an argument for the log. Okay, so if we pay attention, okay, to our root, there is 1 and there is j omega t. There is 1 and there is j omega t. Okay, so here we have 1 plus j omega t. This is the real part, this is the imaginary part. So assume that omega is much less than 1 over t. So what will happen? This means that this term is very small as compared to this. This means that we have only a real part of value 1. And 20 log of this one will be 0. So for very low frequencies, the magnitude will be 0. Okay, assume on the other part, we have omega much greater than 1 over t. So this term will be very large, and this term will be small as compared to this. And if we draw it in the S-plane, we will be almost lying on the imaginary axis. As a result, we might cancel this, and we might consider that we are on the j omega axis. Okay, so this will be again as we discussed in the pole or zero at origin, and it will give us the previous fact that the magnitude contribution will be plus or minus 20, but in the previous case was n. Here it will be q dB per decade. So it will be similar. For large frequencies, the real part will be cancelled, and this will be similar to the previous case, pole or zero at origin, which in this case will be a zero at origin. So it will have the same contribution. So let us go back to our chapter handouts. Okay, here, as I mentioned, we were comparing the frequency with 1 over t, which is less or more. So we call the cutoff frequency, in our case will be, or the corner frequency will be 1 over t. Okay, and as I mentioned, if omega is much smaller or smaller than omega c, it will be 0 dB line, this one. And if omega is larger, then it will be same as pole or zero at origin. It will be plus or minus 20, but there it was, and here it's q dB per decade. So it will be here for 2 zeros, or a repeated zero, here single zero, here single pole, here 2 real poles. So if we draw, in order to validate that we are working in the correct direction, we will draw the magnitude and we will observe this figure. Okay, pay attention to this figure. In this figure, we have drawn the exact curve and the asymptotic curve. Here is the corner frequency I mentioned, it's 1 over t. Okay, and we are dealing with decays, 10 over t, 0.1 over t, 0.01 over t. The ratio between each frequency and its next right or next left is 1 decade. So if we focus on this graph, we see that the asymptotic graph of two asymptotes is very close to the exact. Where is the exact? This is the exact. This is the exact one. Solid line. Okay, this is the exact one. So both of them in this area and in this area, they are coincident. While here there is a few and a very minor difference between the asymptotic and the exact. And based on that, our asymptotes, based on our graph based on two asymptotes, this asymptote and this asymptote, is very close to the true case. So based on that, our approximation is very nice. Based on that, our approximation is very nice. Okay, so this is regarding the magnitude. Okay, if we draw the phase part, here the phase part is drawn. The phase part is drawn. Okay, and as we see, this phase part, it consists of three asymptotes or three straight line segments. This is the first one. This is the second one. And there is one that is connecting them. So there are three asymptotes for the angle or the phase of this pole or zero at origin. And here we are speaking about, not origin, sorry, real pole. Here, if you see here, it's a real root or a pole, real pole. Okay, so the phase graph, okay, consists of three asymptotes. This one, and this one. Okay, and each is valid within certain range. The first asymptote is valid for all frequencies less than the corner 0.1 or 1 decade below the lower frequency, the corner frequency. This is the corner frequency. Here is the corner frequency. 1 over t is the corner frequency. So 1 decade below the corner frequency is this one. And for all frequencies less than 0.1 omega c or 0.1 over t, which is the corner frequency, we have this approximation, which is 0 degrees. Okay. Now, for the second, last one, this is the second asymptotic or asymptote. And it's at minus 90 degrees. Okay. And where is the frequencies that this asymptote is applied? It's for all frequencies larger than 10 over t. What's 10 over t? It's one decade larger than the corner frequency. Okay, where is the third asymptote? The third asymptote is this. Okay, third asymptote is this. So it's a straight line that goes from 0 degrees to 90 degrees. Okay, here it's 0 degrees and here it's 90 degrees, minus 90 degrees. Okay, at this point. So over using 2 decades here, from here to here, 10 over t and 0.1 over t, they are 2 decades. So if we have 90 degrees, negative 90 degrees for this pole for 2 decades, what will be the slope per decade? It will be minus 45 degrees per decade. So we have the change in the angle is 90 degrees, minus 90. And for frequency, they are 2 decades. So 2 decades, we shift from this one, which is 0 degree, to this one, which is minus 90. Over this interval is 2 decades. So the slope will be minus 45 per decade. And in this way, we construct our asymptotic information. So if we pay attention to the handouts, here the phase of this one consists of 3 asymptotes, not 2 asymptotes. For frequencies less than 0.1 omega c, 1 decade below the corner frequency, they are 0, as I mentioned here. For frequencies larger than 10, the corner frequencies, 10 omega c, they are plus or minus 90 q. In our case, minus 90 in this example here, in this case. And if we have 0, it will be plus 90. If we have 2 zeros, it will be plus 180. If we have 2 poles, it will be minus 180 degrees. And in the area between them, from 0.1 omega c till 10 omega c, they will be 45 degrees multiplied by plus or minus q, which is the repeatability, degrees per decade. And if we pay attention to this figure, here it's 0 for all frequencies less than 0.1. And if we have if we have zeros, it's plus 90q. If we have poles, minus 90q. And for this segment, it's plus 45q degrees per decade. And for this case of poles, it's minus 45q degrees per decade. And this is the corner frequency. Okay, so this is the case of the body plot for real roots, whether they are poles or zeros. So if we switch to the case of not pole, this is the case of 0. Here we have 0. The asymptotes will be 0 here, and it will be plus 20 for the magnitude. And for the phase, it will be 0 for 0.1, the corner frequency. It will be 90 for the 0 after 10, the corner frequency. And within this interval, it will be plus 45 degrees per decade. So here we have in the steady state for high frequencies, we should differentiate for low frequencies and high frequencies. For low frequencies, okay, it's always 0. For very, very low frequencies, the contribution will be 0 for phase and magnitude. And for high frequencies, okay, this will be similar to the 0 at origin, and this will be similar to the also 0 at origin. So the real roots for very high frequencies, they will be identical in their behavior in the frequency in the body plot to the poles or zeros at origin exactly. But the difference lies in the low frequencies or intermediate frequencies. This is the intermediate and this is low. For low, zeros, and for intermediate it should have a transition from zero at low to the one similar to the poles or zeros at origin at high frequencies. Okay, now we will switch to the fourth term, which is quadratic poles or zeros. Okay, it might be pole or zero, quadratic, and here we are not dealing with multiplicity. Okay, and in order, we should clarify one point in this regard. So quadratic term, it depends on the value of zeta. So if zeta is greater than 0, this you have taken in the modeling and simulation course, and we have repeated this process in the initial lectures of our course. If zeta is greater than 0, than unity, sorry, we call this system overdamped, and the roots, they are two distinct roots. If they are two distinct roots, then they are covered in the previous case, like two corner frequencies, and we can plot as in the previous case that I have already just covered. Okay, and if zeta is equal to unity, we call this critically damped, and the roots will be real repeated. And also, if they are real repeated, it will be covered in the previous case that I have just discussed with multiplicity q, which will be 2. So the only case that we are dealing here, covered here, it's to be complex conjugate roots, which is under damped case. And for this case, zeta should be between 0 and 1. So the corner frequency for this complex conjugate case, it will be omega c will be omega n. The corner frequency omega c will be omega n. And how can we deal with this case? This case actually is depend on approximations in heavily manner, because here we are assuming that the asymptotes of this curve is similar to the real repeated roots. So we are saying in this case that the complex conjugate, it will have the same graph as real repeated roots with the corner frequency of omega c, which is equal to omega n. So if we have two real repeated roots, as I mentioned, for frequencies less than omega c it will be 0, and for frequencies larger than omega c it will be plus 20 q, and q in our case will be 2, so this means that it will be plus 40 dB per decade. For the phase case, it will be less than 0.1 omega c, it will be 0, and 10 than omega c it will be plus or minus 90 q, and q in this case is 2, so this means that plus or minus 180, and between them we are shifting between 0 and 180 into decades, so it should be plus or minus 90 degrees per decade. So complex conjugate roots, they are based on an approximation which is not valid for all zeta values. Okay, it's not valid for all zeta values. It's good for zeta that is larger than 0.3 or 0.4, but for zeta values that are close to 0, it's not good approximation. Okay, so we here assume that the treatment or طريقة المعالجة تبعت هذا اللي هي الكومبلكس conjugate root هي عبارة عن مشابهة للreal repeated with multiplicity 2. Okay, so if it is a complex conjugate 0, okay, it will have 0 dB line before corner frequency, and it will have plus 40 dB per decade if it is 0 for after omega c. And if it is pole, it will have the same thing, but here it will be minus 40. For the phase, it will be 0 for all cases. and it will be, if it is 0, it will be plus 180. If it is pole here, it will be minus 180. And in between, it should be plus or minus 90 degrees per decade, depending on whether it's a pole or 0. And as I mentioned, this approximation is good for zeta values which are away from zeros. Zeta or delta should be like within the range greater than 0.3. Okay, because as zeta come closer to 0, this approximation is very, very, very poor approximation. And why? Because we have covered similar thing. Do you remember this curve? We have covered before that as we approach 0 zeta, this resonance peak will be very high. So we are speaking about that for values of 0.3 and above, this approximation might be okay. But if it is close to 0, this approximation will be very bad. This is from the magnitude contribution part. And if it is from the phase contribution part, if you pay attention to this figure, we see that the linear transition here, let us observe that we have the transition between 0 and here, which is minus 180. But the speed of the transition and the curve is different for different values of zeta. As zeta become closer to 0, then there is a steep transition. There is a steep transition in the angle. While for zeta, which is away like 0.5 or 0.7 or 1, which is will be repeated, the transition will be more or less linear. So this is why I said that our approximation is valid for zeta values between 0.3 and 1, or less than 1, because 1 will be repeated, between 0.3 greater than 0.3 and less than 1, while values smaller and closer to 0, it will have a very bad approximation, because at zeta which is equal to 0, it will be, the transition will be like this. It will be like a negative step function. Negative step, which is discontinuous here. So our approximation is valid for values away from 0, which is good. It's considered as linear transition between here and here. Here 0, here 180, and here is the linear transition between 0 and 180 for values of zeta within this range. For values of zeta less than within this range, less than 0.3, it will have a very sharp transition. The transition will be very sharp and our approximation will be very bad. So let us switch to the final term in among the 5 basic factors. The 5th term is the pure delay, e to the power minus j omega td. Td is the time delay. So if you remember, there is Euler quantity that you can formulate this exponential as sine and cosine, and if you find that its value, it will be unity in the normal scale, and if we calculate it in the dB scale, it will be 0. So the magnitude contribution of any delay is 0 in dB and unity in normal scale, and its phase will be minus omega td. It will be the argument without j, minus omega td without the j, in radians but it's in radians. And how can we convert it? If we convert radian to degrees, it will be minus 57.3 omega td degrees. So this is what we need, because we are dealing with everything in degrees. So the delay, it has 0 magnitude contribution, while it has a phase or angle contribution of minus 57.3 omega td, and it's dependent on omega. It's a function of omega. It's a function of the frequency omega. It's not constant. Okay, so this page summarizes all of the previous factors that I have previously discussed. Okay, here we have k, constant gain k, and we assume that k is greater than unity. So this is why we have here it will be a constant of positive dB and its phase will be 0. If we have a simple 0 of corner frequency omega 1, the corner frequency is omega 1 here, so before the corner frequency it will be 0 and after it will be plus 20 dB per decade, and the phase will be for 1 decade below the corner frequency it will be 0, 1 decade after it will be 90, and in between it will be plus 45. So this is the case of 0. Similar thing but with negative signs for pole, real pole. So for less than corner frequency it's 0 and higher than corner frequency it will be minus 20 dB per decade. This is for the magnitude. And regarding the phase, 1 decade below the corner frequency 0, 1 decade after it will be minus 90, and in between it will be minus 45 degrees per decade. The final one in this table, or not final one, if we have a pole at origin, so we have for this pole at origin we have a constant slope of minus 20 dB per decade for all frequencies. It has no corner frequency. This one has no corner frequency, so the slope is constant for all frequencies, which has minus 20 dB per decade, and its phase is, as I discussed before, minus 90. So if we continue and take the last one, which is complex conjugate roots, and zeta within this range, okay, and as I said it's special case of the third case with multiplicity of 2, so it will be for lower than the corner frequency 0 and higher than the corner frequency it will be minus 40 dB per decade, because here we have pole, and for the phase part it will be 0 1 decade below the corner, it will be minus 180 1 decade after, and in between it will be minus 90 degrees per decade. Okay, so I have summarized all of the previous sorry for the interruption. I have summarized all of the previous 5 cases in this document, which I have already sent to the coordinator of the course. Okay, I have sent it already today to the coordinator of the course. So here we have the constant gain K, but I am assuming that it's positive because this is the normal case. I am assuming that it's positive constant gain K, and this is pole or 0 at origin, and here real poles or zeros of multiplicity Q, and here complex conjugate roots, and here is the pure delay. And here regarding the corner frequency, for corner frequency it happens if we have 2 or more asymptotes for the magnitude graph. If we have 2 or more asymptotes for the magnitude graph, okay, then we have corner. So if you pay attention to this number of asymptotes in the magnitude graph, here 1 1 1, so the graph is one asymptote. So we don't have a corner frequency, because corner frequency is the intersection between 2 asymptotes. So if you have one asymptote, we don't have a corner frequency. This is why it does not exist here and here and here. So 3 factors out of the 5, the gain, the poles and zeros, and the delay, they don't have corner frequency. So 2 only, they have corner frequencies. What are they? They are real roots, real poles or zeros, or complex poles or zeros. or the complex poles or zeros. So this is the case where we have this one, okay, and this one, okay, which are poles or zeros at origin. Okay, and I have covered here in this table all of the details that I have previously discussed. Okay, so I have mentioned that. Sorry, it seems that this file is not working with me. So I have already sent it to the coordinator. You might please go through it. It's a summary of what I have discussed before. You might take it from the coordinator and study it. Okay, because it's not working okay with me. It's always shut down this folder, and we are ready in the next lecture to cover the drawing steps or how to build the body plot for any general loop transfer function. Thank you, and wish that you understand everything. Thank you.